Today we're going to look at oscillations. This will include what are the conditions to get oscillations, what are the conditions to get simple harmonic motion, what are the motion graphs when you have simple harmonic motion, what happens to the energy, and then what is phase and phase difference.
So what is an oscillation? Well, just something that moves back and forth. However, there are a few characteristics of any force that produces an oscillatory motion. We say that we have to have a restoring force. And what's meant by a restoring force? Well, it simply means that there's got to be an equilibrium position, and that's a place, it could actually be a region, where there's no net force. And our force will always have to be such that if the object is over here on this side of equilibrium, the force will be back towards equilibrium. If the object is over here on this side of equilibrium, then the force is going to be back towards equilibrium. So to be maybe a little more mathematical, if we defined our displacement as being from that equilibrium position, then here you'll see that if the displacement is to the right, the force is to the left. If the displacement is to the left, the force is to the right. So F and the displacement from equilibrium are in opposite directions. Now perhaps the two most important quantities to describe an oscillatory motion would be the frequency and the period. The frequency is simply the number of cycles, complete to-fro motions, that our oscillator makes every second. So it's the number of cycles per second. So it's got to be at 2 followed by a fro motion, so that it comes back to its original place. That would constitute 1 cycle. And the period is the number of seconds it takes for 1 cycle. If you just consider the units here, the frequency is cycles per second, whereas the period is the seconds per cycle. Just based on the units, you're likely to guess a reciprocal relationship between these two quantities. And typically here we'd use a small f for frequency and a capital T for period. And the reason that we use a capital T is because this is an amount of time. So by using a T, it reminds us it's the period that's the one that's an amount of time. So we have a reciprocal relationship between period and frequency. That is to say that the frequency is equal to 1 over the period, and if you rearrange that, the period is equal to 1 over the frequency. So for instance, let's say your frequency is 2 cycles per second. So that would mean you'd go there and back 2 times in 1 second. Your period would therefore be the amount of time to get to here, which would be half as much, 0.5 seconds, or 1 over 2 seconds for that cycle. And here you see the reciprocal relationship. Frequency is 2, period is 1 over 2. As always, we begin with the simplest type of thing first, and the simplest type of oscillation is called simple harmonic motion, or SHM for short. Classical example of simple harmonic motion would be a mass on a spring. So we can imagine we've got a mass on a spring, and it would oscillate back and forth about some equilibrium position. Let's say this is our equilibrium position here. This is equilibrium. And it's conventional to say that the position is 0 at equilibrium. So that, let's say we displace our mass to the right of equilibrium, and typically we'd call that displacement vector x, though in the previous slide I called it delta x. But as long as we take our equilibrium position to be x equals to 0, it's better to write it this way, simply as x as your displacement vector. Of course, if I displace my mass to the right, there's a force from the spring pulling that mass in the opposite direction. Let's call that the force F. Now, if we're going to get this simple harmonic motion, that means that if I double how far I push my mass to the right. So I'm going to make this twice as big of a displacement. If I do that and we're going to get simple harmonic motion, then it will have to be the case that I double the displacement, I also double the force. I get 2 times as much force. And of course, if I triple the displacement, I get 3 times as much force, etc. And of course, that's just a proportional relationship. We would say that the magnitude of the force is proportional to the magnitude of the displacement. So I might write that as the magnitude of the force is equal to a constant times the magnitude of the displacement. This k would turn out to be the spring constant. Now we might choose to write this equation in terms of vectors with direction. So we'd have a force vector equal to k times the displacement vector. In terms of the direction, well, they're just opposite. If I displace my mass to the right, the force is back to the left. If I displace to the left, of course the force is back to the right. So we can simply put a negative sign in here to say that the directions of the displacement and the force are opposite. And we can take this a little farther. Typically, we don't write it in terms of the force, we write it in terms of the acceleration. So for instance, in this case here, I've got that constant k, which represents a spring constant. But what if we've got a pendulum? Pendulums execute simple harmonic motion, at least for small oscillations, and they don't have any springs. So what we typically do is we write this in terms of acceleration. And to do that, all we need to do is divide both sides of the equation by mass. F over m, that's just acceleration by Newton's second law. And that will equal a negative, a constant k over m, but of course we don't like the k's because that's the spring constant. We don't always have springs. We write this as omega squared, and that omega turns out to have a physical meaning. Omega is called the angular frequency, or sometimes the angular velocity. Its units are radians per second. Turns out, and we'll learn this later, a radian is a fraction of a cycle. So this angular frequency is going to be proportional to the regular frequency, which is the number of cycles per second. And it turns out the constant proportionality is equal to the angular frequency squared for any object in simple harmonic motion. So this proportional relationship between acceleration and displacement, or between force and displacement, is the defining condition for simple harmonic motion. That is, if we have SHM, simple harmonic motion, then the acceleration of the mass will be proportional, but opposite in direction to the displacement from the equilibrium position. And we might represent that all graphically. If we do a graph where we plot the displacement against the acceleration, which of course is equal to the force divided by the mass, then we've got a proportional relationship. That means we've got to get a straight line through the origin. But it's going to have a negative slope this time, because the direction of the acceleration is always opposite to the direction of the displacement. So a graph of acceleration versus displacement will be a straight line through the origin with a negative slope. When we were studying kinematics, we did motion graphs, graphs of displacement versus time, velocity versus time, and acceleration versus time. And now we'd like to do the same thing for simple harmonic motion. So I'm going to create a little graph here. On the vertical axis, I'll put the displacement, and on the horizontal axis, I'm going to put the time, just like we did for the motion graphs in kinematics. Now I could choose any point in the motion of the mass as t equal to 0. I'm going to choose the point where the bottom of the mass is right at equilibrium here and heading upwards. So that's going to be t equal to 0. So then it goes up from there, reaches a max, comes back down, goes back up, and then just keeps repeating that pattern, something like so. And here we've got one complete cycle. So the mass would be exactly back at the same point here, and it would also be heading upwards at that point. So this would be one period, one complete cycle. And then after 2 periods, 2 complete cycles, the mass would be back to the same position again and heading in the same direction. This distance right here, it has a special name. The IB uses an x naught to represent it. It's called the amplitude. So that x naught, it represents the amplitude. And the amplitude of the oscillation is defined to be the magnitude of the maximum displacement. So the amplitude is always going to be positive because it is a magnitude. Now what we're going to do is create the velocity time and acceleration time graphs from the xt graph. So here was our xt graph. Just had this sinusoidal shape, and you'd repeat this pattern. And the period was right here. If we do a vt graph, of course, a velocity will equal the slope of an xt graph. As we kind of transfer our displacements into velocities, the slope of the xt is going to become the value on the vt. And then if we want to make an acceleration time graph, we use the same principle, because we know acceleration is equal to the slope of a vt graph. So once again, we can use this idea of slope becomes value. So on the xt graph, we have a fairly high positive slope here. So our vt will start with a high positive value. When we get to here, then the slope is of course 0. No slope at all. That means the velocity must be 0 at this point. Here we've got a strong negative slope. So we'll get a strong negative value. Might be about here. Here, once again, we have 0 slope, so we're going to go back to a 0 value. And then we'll be back to a positive slope here. And we'll get that sinusoidal shape. It's going to look like so. And just keep repeating the pattern. And then we can do the same trick to get our AT graph. The slope here on the VT graph is 0. So our acceleration must start out as 0. Then we've got a fairly strong negative slope about here. Back to a 0 slope, so a 0 value. Back to a positive slope, so a positive value. And then back to a 0 slope. Make that a smooth curve between those dots, a smooth sinusoidal curve. It's going to look like this. And in the same way that we defined an amplitude here so that the displacement oscillated between negative x naught and positive x naught, we can have the velocity oscillating between a maximum negative speed and a maximum positive speed. And we can have the acceleration accelerating between a negative value of the magnitude of the maximum acceleration to a positive value of the magnitude of the maximum acceleration. And also notice here that the xt curve and the AT curves are kind of upside down versions of each other. And that's because you'll recall that acceleration is equal to negative omega squared x. So this negative sign means acceleration and displacement are in opposite directions. So when the displacement is positive here, the acceleration is negative, and vice versa. So the acceleration and displacement are kind of upside down versions of one another. What we'd like to do now is take a look at the energy transformations that occur in simple harmonic motion. And we'll go back to our classical systems, pendulum, mass on a spring. So the first thing to realize is that in any simple harmonic motion, you've got 0 speed at the endpoints. So for our pendulum here, here's the endpoints. You have 0 speed. It's a turnaround point. And that means you have 0 kinetic energy. And that implies you're going to have maximum potential energy. In this case, it's gravitational potential energy, and you can see that the ball is at its highest point at the endpoints. When the ball's at its lowest point, that's when you're going to have maximum kinetic energy. So we have this constant transformation between potential energy, gravitational potential energy, and kinetic energy. It just kind of sloshes back between the two forms. Maximum kinetic energy in the middle at the equilibrium point, maximum potential energy at the endpoints. And you see it's exactly the same here for the mass on a spring. It's oscillating between two endpoints here, and it's going to have zero kinetic energy, maximum potential energy at those endpoints. Maximum kinetic energy in the middle at the equilibrium point. And the only difference between this and the pendulum is that in this case our potential energy is elastic potential energy. We're stretching and compressing the spring. Whereas in a pendulum, it's gravitational potential energy. The pendulum bob is getting higher and lower. Now if we take a mass from the spring and make it vertical, then our potential energy, once again, it's going to be maximum at the endpoints. And you're going to get maximum Ke at equilibrium, where the forces balance out. The difference with the vertical mass on the spring is that that potential energy has two forms now. It's going to have some gravitational potential energy and some elastic potential energy. But it's still the same overall idea. Maximum potential energy at the endpoints, maximum kinetic energy in the middle, total energy remaining constant throughout the cycle. We can also plot all these energy transformations. Let's see what the graphs are going to look like. And I'm going to start with actually a velocity time graph, the same velocity time graph that I did a few slides back. And you'll remember in the velocity time graph, if we started at t equals 0 with our mass at the equilibrium point and we gave it a positive velocity, then the graph looked like this. After a quarter of a period, it would reach the end point. Then it would turn around, go in the opposite direction, come back, there's the end point again, and then it would reach a maximum value again as it went through the equilibrium point. So there's our VT graph. Now if I were to plot V squared, of course all the negative values down here would become positive. So if I did a V squared graph, it's going to look very similar. This negative portion is going to get kind of reflected upwards. It doesn't have quite the same shape because it's a V squared graph. And the reason I wanted to plot V squared was because if I take V squared and I multiply it by a constant 1/2 m, then I'm really plotting the kinetic energy. So this here is a graph of the kinetic energy versus time. That's what it would look like. Now the total energy, the sum of the kinetic and potential energy, it has to remain constant by the law of conservation of energy. And being as in the equilibrium positions, all the energy is kinetic energy. Therefore, the total energy is going to equal the kinetic energy at the equilibrium point. So this is what our total energy curve would look like. For the potential energy curve, it's going to look like this, more or less. And I know that because the potential energy plus the kinetic energy has to add up to the total energy. So for instance, if I take some instant in time here coming up, and I add the potential energy here, plus the kinetic energy here, I add those two values up, I've got to get that total energy value. So that's what our potential energy curve has to look like. I might also plot these on a graph that has energy along the vertical axis and just displacement along the horizontal axis. So of course my displacement would range between that negative value of the amplitude and the positive value of the amplitude. Right at the end points, of course, my potential energy would be a maximum. So I get maximum values for the potential energy at the endpoints. And of course it drops down to zero potential energy in the equilibrium point. And so the curve for potential energy looks like that. The total energy, once again, it remains constant. And being as you've got all potential energy at the endpoints, the total energy will have to equal the potential energy at the endpoints. And then once again, we can play the same game to get the kinetic energy. I've got to make a curve such that when I add the potential energy and the kinetic energy together, I get the total energy. So at this displacement, if I add that potential energy value to this kinetic energy value, I should get the total energy. A very important quantity when you're dealing with oscillations, or really any cyclic phenomena, is something called the phase. And the phase is simply a way to keep track of where the mass is within a cycle. And rather surprisingly, it turns out to be an angle. But if you think about circular motion, it's also cyclic. And we could keep track of where the mass is within a cycle by using an angle here. And that angle could range anywhere from 0 to 360 degrees. Or if we were using radians, it would vary anywhere from 0 to 2 pi radians. We're going to use really the same angle to keep track of where the mass is in an oscillation. So we might describe its phase as being 0 degrees when it's at the equilibrium position and heading upwards. When it reached the end point, it would have gone through a quarter of a cycle. And so we'd call that pi over 2 radians, or 90 degrees. Then it would continue on its cycle, complete another quarter cycle, and we'd call this point in the cycle pi radians, or 180 degrees. And it would continue on, go through another quarter of a cycle, and then it would be at 270 degrees, or 3 pi over 2 radians. And then of course it would come back up, return to its original position, repeat the cycle, and you'd repeat the phase angles all over again. So it's just an angle that keeps track of where the mass is within its cycle. When it comes to wave interference, it turns out the phase difference is a lot more important than the phase. And what we mean by phase difference is if we've got two objects that are moving exactly together, then there's no phase difference. We would say that they were in phase. Or we'd say it was a 0 degree phase difference. If we've got two masses like here, where they're doing exactly the opposite, one's at the very top of its motion when the other's at the very bottom of its motion, then we would say that they were out of phase. Or we'd say that there was a 180 degree, or alternatively pi radian, phase difference. And notice that that's the maximum phase difference that we can get. You can't get a phase difference bigger than 180 degrees. And that's because if we have, say, two objects on a circle, here's one, here's another, and we talk about the angle between them, well, we could talk about this angle, or we could talk about this angle here. But the smaller angle there is always less than 180 degrees. So we always say that the phase difference is always less than 180 degrees. Two things can never be more than 180 degrees out of phase. Now this isn't going to be very accurate, but see if you can estimate the phase difference between these two pairs of oscillators. So pause the video, try the question, come back for my estimates. This first one here, I'd say the phase difference is getting pretty close to 90 degrees. And I noticed that as one gets to an endpoint, this one's in about the middle. So if you have one at the endpoint and the other in the middle, that's always going to be about a 90 degree phase difference. These two are pretty close to being in phase. They're just a little bit out. Certainly less than 90 degrees. I'd even say it's less than 40 degrees. I'd say somewhere around 30 degrees of phase difference as a not bad estimate. Now certainly in the second example, the phase difference is quite small, and we might make a rough guess, maybe 30 degrees, 40 degrees, something like that. What I did was I measured the time for one cycle. It turned out to be about 5 seconds for one cycle. And then I measured the time it took for one mass to hit the bottom and then the second mass. And that turned out to take about 0.6 seconds. So my phase difference would be equal to 0.6 divided by 5 times 360 degrees. So I'm getting an answer there to one significant digit of about 40 degrees. One other very important fact about simple harmonic motion oscillations is that they're isochronous. Isochronous simply means the oscillations have the same period. They take the same amount of time to swing back and forth, regardless of amplitude. So if I release a pendulum, like the blue ball here, with a greater initial amplitude, it has a longer distance to go back and forth. But it also has greater acceleration, and that gives it a greater average speed, and the two factors kind of cancel each other out. So you can see the blue ball here, it catches up to all the other balls after a quarter of a period. And that's really critical in the operation of a grandfather clock, which is really just based on a pendulum. If I take a pendulum and let it swing for a while, then there's a little bit of friction, and the amplitudes will get smaller and smaller. However, the period remains exactly the same, and that's critical to a grandfather clock being able to keep track of time accurately. Okay, a few IB questions for you. Pause the video, try the question, come back for the answer. So, correct graph of acceleration against displacement. Remember, acceleration is in the opposite direction as the displacement, and they're proportional to one another. So the correct answer here is graph A. Another IB question. Pause the video, try the question, come back for the answer. Okay, so if the cart's in equilibrium, equilibrium really just means that the net force has got to be 0. And if we have our cart right here in the center, both of these identical springs are going to be stretched, and they're both going to pull in opposite directions with the same force. So those forces will cancel out, and that means that the point O is the point where there's no net force, and that's the equilibrium point. Okay, a third IB multiple choice question. Pause the video, try the question, come back for the answer. First, let's look at the period. This is simple harmonic motion because it's a mass on a spring. And that means we're going to get isochronous oscillations, which means T has to be the same regardless of the amplitude. And that means we can eliminate choices C and D. So now let's look at the energy. The total energy is going to be equal to the elastic potential energy, the potential energy at the endpoints. And of course, at the endpoints, our displacement is equal to this capital X. So our elastic potential energy would be given by 1/2 times the spring constant times this capital X squared. That's our total energy E. Now in the second case, where our amplitude now would be this capital X over 2, then in this second case, we would get 1/2 K times capital X over 2 all squared, which is going to equal 1/4 of 1/2 K capital X squared, which is 1/4 of that original energy. So the correct answer here is answer B. Okay, let's summarize the key ideas from the video. First thing, we talked about what was needed in order to get oscillations, and we talked about a restoring force, which was just a force that was directed back to equilibrium. And equilibrium was simply a point where there was no net force on the object. The second thing we talked about was under what conditions would our oscillations be simple harmonic. And we basically said there, well, they'd be simple harmonic if we had a restoring force that was proportional in size to the magnitude of the displacement. And that kind of led to this defining equation for simple harmonic motion, which said that the acceleration was proportional in size to the displacement, but in the opposite direction. And then we began to graph the motion. We did line graphs of displacement, velocity, and acceleration versus time. And all of our graphs would have this sinusoidal shape, but they would be shifted relative to one another. So if our displacement time graph, say, looked like so, then our velocity time graph would look like so, and our acceleration time graph would kind of be a flipped upside down version of our displacement graph, like so. We also defined the amplitude on the displacement time graph. We then did graphs of energy versus both displacement and time. Our graph versus displacement had a potential energy, and you had a maximum potential energy at the endpoints. It had a kinetic energy, which was maximum at the equilibrium point, and a total energy that was a constant value. We then talked about phase and phase difference, and the phase told us where the mass was within its cycle. Whereas the phase difference told us whether two objects were in sync or how far out of sync they were. And that's all for today, folks. Thank you very much.